In section 1.2, we're going to take a look at patterns. And as with a lot of the sections we're going to do, they kind of start out with a few definitions here and there, and this is one of those sections. And so to start with, we're going to look at a little vocabulary. Conjecture is a statement or a conclusion that has not been proven. A counterexample is something that proves a conjecture false. And then these last two are something that are actually very specific to mathematics. They're inductive and deductive reasoning. We do see them in other places in sciences as well, but this might be the first time we've heard them defined specifically. Inductive reasoning is a method of making generalizations based on observations or patterns. And deductive reasoning is the use of mathematical axioms, theorems, definitions, or undefined terms assumed to be true and logic for proof. So inductive reasoning is the kind of thing that usually gets us in trouble, right? So it was hot today, and it was hot yesterday, and it was hot today before, therefore it's going to be hot tomorrow, and maybe it's not, right? That's what inductive reasoning says. It says there's a pattern of something that's happened, and I'm going to make a decision based on that pattern. Sometimes that works out for us, and sometimes we find ourselves wishing that we'd, worn something a little warmer or whatever. So that's inductive reasoning. Deductive reasoning is more concrete, and we'll see how these are used in patterns in mathematics and the comparison between the two today. Okay, and a reminder, if you didn't print them, these are printed, or they're out in printed form for you to print on Canvas. If you haven't been printing them, haven't printed them yet, feel free to do so. Okay, so a few more sequences. So sequences are an ordered arrangement of numbers, figures, or objects. Sequences and patterns are used with kids clear down to preschool. So what do they look like when you're in preschool? They look like something like this, like triangle, square, what comes next? Red, blue, red, what comes next, right? They're patterns like that. As we get a little bit more under our belt in terms of education, they might start looking like the actual patterns of numbers that we're going to be looking at today. And between today and Wednesday, there's also some sequences that have both imagery and numbers, and there's a relationship between the two. Now, a recursive formula is a formula based on the pattern established after one or more consecutive terms are given, and a rule that shows how to obtain each successive term of the sequence. So that sounds really complicated, but it goes something like this. So I'll give you an example. So you've got a sequence, right? It doesn't end. 2, 4, 6, 8. So this is a few of terms in the sequence, and then they tell you how you get to the next term. You get to the next term by adding by 2. Right? That's what a recursive description is. You have the first few terms, maybe you only have the first couple of terms, sometimes even, but then it tells you a description of how to get the next term. Now, an nth or a general term is a formula that can be used to find any term, namely the nth term in the sequence, with no prior terms needed. So for example, if I were doing a recursive formula and somebody said, now find the 100th term, you're probably not going to be real happy, because you're not going to want to add 2 repeatedly 100 times to get where you want to go, right? Like that's not real helpful. Okay, so recursive formulas do a really good job of establishing patterns and giving you the first, X number of a few of them, right? But we don't want to go too far with a recursive formula. An nth or a general term formula is much nicer in general to have. For example, you have an equation that says something like this, 2n. Well, if this is 2n, and it means that I want to find the nth term is the 100th term, I can just put the number 100 in here, and I know it's 200. This is the general form for this sequence, right? So like if I put in the number 1, 2 times 1 is 2, that's the first term. And if I put in the number 2, 2 times 2 is 4, that's my second term. So there's 2 different ways of thinking about formulas, and we will use both of them. An arithmetic sequence is the example that I just gave you. It's a sequence in which each successive term is obtained by the addition of a fixed number. Now, that addition could be the addition of a negative. Because it doesn't have to be adding a positive number. It could be adding a negative number and work just fine as well. So, for example, if I had, sorry about that. We'll make one up so that it's got a negative since I mentioned it. Let's go with that. I am adding a value every time here, but it is a negative value because the sequence is getting smaller. What negative value am I adding to get over here? -3. Now, you're welcome to think of it as subtracting 3. That's fine. It's neither here nor there. But the definition, calling it addition of a number, works if you're adding a negative. Okay? This negative term right here, this -3 here, is called the common difference. Okay? It is the fixed number that's added or subtracted to get the next term each time. And if you can identify what it is, you can continue the pattern, right? Oh, look, it's -3. Well, I can find the next one, I can find the next one, I can find the next one. But I probably don't want to keep doing the next one sort of a patterning for 100 terms, right? But I have that ability to find the first few. So the common difference is what that value is called. The other type of sequence we're going to talk about 2 more, but the other big one here is geometric sequence. So a geometric sequence is a sequence in which successive terms are obtained from the previous by multiplication by a fixed number. Okay, and again, the multiplication doesn't have to be by a positive. It could be by a negative. It doesn't have to be by a whole number. It could be by a fraction. Okay, so it can be multiplication by anything and still fit this definition. Now, most of ours are going to be multiplication by a positive number. Like, that's what you're going to see the majority of. But the definition is open-ended. It allows for other things. Do you need me to go back, Savannah? Okay, go ahead. Got it? Okay.
I thought I was just getting it wrong because the 2 blanks are the same.
Oh, sorry. All right, and so let me give you an example. Let's see which one I have written down. Oh, we'll do one it is kind of complicated. Why not? This is a geometric sequence. Can you tell what you're multiplying by each time? Do you have an idea, Caleb?
-3.
You're close.
I know it's something to do with 3.
It is something that has to do with a 3, Brady. 1/3. Yeah, it's multiplication by 1/3. Yeah. So if I multiply by 1/3, or you can think of that as being division by 3, right? And that's fine. You can think of it as dividing by 3, not a problem. But division by 3 is the same as multiplication by 1/3, so it fits in with this definition of a geometric formula. This number 1/3, then, this is the fixed number, is called the common ratio. So common difference when we add or subtract, common ratio when we're multiplying, dividing, common difference when it's a arithmetic sequence, common ratio when it's a geometric sequence with multiplication. All right, the last one that we're going to look at in terms of identifying a sequence is Fibonacci. Fibonacci is very interesting, and it occurs all over nature. So I have a feeling that you probably will see it show up in one of your science classes. Probably earth science is probably where you'll see it show up. I'm not sure. But Fibonacci sequences are very common. So they are not arithmetic and they are not geometric. So they are non-arithmetic, non-geometric. And they do follow a different pattern common in nature. And let me actually write down for you the Fibonacci sequence, at least the first few terms. Has anybody ever seen or heard of the Fibonacci sequence before? Caleb, you have? Okay, you have. A few of you have? Okay. Do you remember how it is that you get successive terms? Because it's not addition and subtraction in the traditional sense like we just did, or multiplication. Yeah?
It's the previous 2 terms added together.
Yes. So if you add 1 plus 1, you get 2. And if you add 1 plus 2, you get 3. Take another one. If you add 8 plus 13, you get 21. So could we use that idea to find the next one? Sure could. What if we add 13 and 21 together? What would come next?
34.
It would be 34. Okay? So we would continue that process. You add the two terms in front of it and it becomes the next term. And this shows up in, what I mean by in nature is it shows up in the shells and the way shells work. It shows up in, I think it's
Sunflowers.
how sunflowers grow.
I know
Is that what it
there's
is?
some flowers.
Some flowers. I hear what you're saying.
can't know if-
I think it shows up in rings of trees. Yeah.
One example of it, if you use that as a gambling strategy on a roulette wheel, you're scientifically proven to win eventually a lot of money.
Interesting. Okay. Please don't gamble. Okay. Let's not. But I'm glad that that's a great example from another area that I have not known about. All right. You need a definition that feels a little bit ill-placed, but we're going to need it in a minute, so we're putting it here. A to the power n. So if n is a natural number, then a to the power n means a times a times a, all that multiplied by itself n times. And so that, we encountered this idea with addition into multiplication last time with Gauss's method, right, where we said repeated addition is multiplication. This is repeated multiplication, and it turns into powers. So the same idea. And then there's a couple things here at the end that we need some details of. If n is equal to 0, and we don't have a base that's 0, right? So this is not going to work. You've got 0 to the 0. That's not going to work, okay? But anything else to the power of 0 is equal to 1. So 5 to the 0 is 1. 7 to the 0 is 1. Negative 2 to the 0 is 1, right? All those values to the 0 power are going to be equal to 1. Now, this seems like a funny definition to show up in the middle here. You'll see it come into play in just a second. But, all right. Everybody good so far? Okay. So we're going to do an example. And there's two, actually more than one example here. But each of these, we're trying to decide. We're going to list the three terms in the sequence. And then we're going to identify if the sequence is arithmetic, geometric, or neither. And then we're going to find the general term for the sequence. Okay? So this is what we're looking at. The first piece, everybody always does really good on. Right? Just find the next three terms. So take a second, see if you can figure out what the pattern is for A and B. Ignore C for the moment. Figure out what the pattern is in your mind. What's being added, subtracted, multiplied, divide. What is it that you're doing? And get the next three terms. Okay? After you do that, compare with somebody nearby. Just see if you've done that part right. Did I get the right next three terms? So if you're done writing, check in with somebody nearby. Ask them, what'd you get?
I'm breaking a lot.
Okay, 1, 4, 7, 10. What's next? 13, 16, 19. Everybody agree? Excellent. Is this arithmetic or geometric?
What's the difference again?
Okay, arithmetic means you added or subtracted something. We say added, but you can think of it as subtracted. Added something. Geometric means you multiplied or divided by something. So which one's this one? This is arithmetic, okay? So this is sort of like I, and this is double I. We've got this is arithmetic. Okay, we'll get back up to the general term part in a second. Let's do the next one. 3, 6, 12, 24, then what?
48.
48.
96.
92. Okay, everybody good? All right, so this is the sequence. Arithmetic or geometric?
Geometric.
Geometric.
We multiply by 2 each time.
Yes, we multiply by 2 every time. Okay, so the finding the general term part is the part that always trips people up. I will tell you that there is formulas in your book to do this. I shy away from formulas because, number one, I don't really feel like that's a very useful strategy for you guys to be thinking about, how do I do this? I got to go find a formula. There's no need for a formula to do what we're about to do. There's not. But there is a need to understand what's creating this pattern. Okay? So, RJ mentioned we multiplied by 2 on this one, right? Okay, so that's important. That's part of what we need to know for our pattern. So let's go back up to the first one. What did we do for the first pattern? We added 3, I think, right? Okay. Okay. The arithmetic one is easier to create the formula for and sort of understand all the pieces of where they come from. So we are going to start with that one. That's the first one. Okay. So last time when we talked about Gauss, we talked about the fact that what he did is instead of having to add together lots of things that are different, he changed it so that it was adding together lots of things that are the same, right? We had the number 100 and we added together 100 plus 100 plus 100. We said that's easier. Okay? And we talked about the fact that repeated addition is the same as multiplication. So everybody remembering this. Okay? So this is what an arithmetic sequence does. It's repeatedly adding 3. We add 3, we add 3, we add 3. We are repeatedly adding 3 every single time. Yes? Okay. So with an arithmetic sequence, that means is that we are actually multiplying 3 times the number that we want for the term. Now, that doesn't quite get us there most of the time. It could. If this sequence said 3, 6, 9, 12, whatever, 3n would do it for us. And we'd be good to go. But it doesn't quite say that. I mean, we're still adding 3 every time, right? We're skip counting by 3s, right? That's what we're doing. But we're not starting at 0 and then going to 3 and then 6 and then 9. We're starting at, was it 1? At 1. Okay, so what would happen if I plugged the number 1 in here? What is 3 times 1?
3.
It's 3. But it doesn't start at 3. It's supposed to start at
0.
At 1. This one's supposed to start at 1, right? So what I have to do is I have to remove 2 to reset it back to where it should have been starting. I need to move it back. I want to be able to plug the number 1 in and get 1 because it started at 1. Now check it out. What happens when you plug the number 2 in?
Multiplies to 6 and then subtract by 2.
You get 4, right? What if we plug number 3 in? 3 times 3 is 9 minus 2, 7. So you can check several terms. That's fine. But the general idea is this. The repeated addition is a multiplication factor. That's why that's happening. It's the common ratio, or excuse me, the common difference part. Okay? And then we add or subtract to make sure that it's starting at the right place. Yes?
So, how did you know to make it -2?
Because if I don't make it -2, it's already at 3, and I need to give it a subtraction to get it back to the number 1. I'm trying to shift it back to 1. So I'm asking myself, what do I need to add or subtract to make this 3 into a 1? And the answer is -2. You subtract a 2.
So if you're adding or subtracting something, like, you just multiply?
You multiply by the common factor, right? The common difference that we're doing. So whatever that common difference is. So like over here, when I gave you this one, that's not it. Well, actually, we can do this one. This will be fine. So this one, I was adding -3 every time, right? So it would have been sorry about that. It would have been -3, N or X or whatever letter you're using. But if I put a number 1 into this, I'm going to get -3. I don't want to get -3 at the beginning. I want to get 10. Well, that means I'm going to add something because it's too small. Right now it's a -3. What would I have to add? I'd have to add 13. Now, there is one other way to think about it. Let me show you that as well in case you like this one better. This is a really good place in which to do this. If I continued this pattern and I went backwards, what would come before 10? That'd be the 13. Now, the one that I just did, if I continue this pattern and went backwards, what would come before 1? -2. Again, that's the number I'm adding or subtracting on the end. So if you like that sort of a picture better, that is the value we're always going to add or subtract on the end. It's the number that comes before the value in our sequence. Yeah. Okay, you ready to look at geometric? So geometric means that I'm multiplying by something in common every time. And in this problem, it's 2. So I'm multiplying by 2, and I'm multiplying by 2, and I'm multiplying by 2, and I'm multiplying by 2. Repeated multiplication is powers. That's why this came into play when it did. Repeated multiplication gives me powers, right? So not supernatural powers, like just, the ordinary ones in math, those kinds of powers. Okay, so the way that this works then is that common ratio, 2, is raised to a power, n. And what we do is we take 1 away from n to reset it back 1, kind of like we reset the last one back when we're subtracting 1, okay? And if these were all powers that had actual 2s, like this does not start at 2. This starts at 3, yeah? So what we do to make sure it's starting at the right place here is that we actually multiply it by 3 at the beginning.
By the first number?
Whatever the first number is gets multiplied at the beginning. So this is the first number at the beginning, and then it's the common ratio, and n minus 1 sets it back. Let me show you how it works. Let's say we started at n equal to 1. What happens when I put a 1 in right here? What's 1 minus 1?
0.
0. What's 2 to the 0?
0.
1. It's 1 right here. Anything to the 0 power is 1. Okay. So this will become a 1. And what's 1 times 3? 3. Now that's not a very exciting one. Let's do something a little more exciting. Let's do n equal to 3. So n equal to 3 should give me a 12, right? Let's try n equal to 3. 3 minus 1 is 2. 2 squared is 4. 4 times 3 is 12. Okay? Now, all that just multiplying and stuff we just did in our head, that's just checking to see that it actually fits the description we're talking about. Right? It's a good thing to check. But it's not absolutely crucial to write down the answer and then, you don't have to show that work, I guess. That's how I should say it. You don't have to show that work.
So the n minus 1 will always be the power?
It will. N minus 1 will always be the power. Yep. And the reason is because you're setting it back to being the first term, and then you're multiplying by that first term on the outside. Okay. Now, these problems are both the same type of reasoning. Are they inductive reasoning, or are they deductive reasoning? So I'm going to flip us back so that we can see where we described them. Here they are. Inductive reasoning is making generalizations based on observations or patterns. Deductive reasoning is the use of mathematical axioms, theorems, or definitions, undefined terms, assumed to be true in logic for proof. Can you tell which one we were doing on those problems? What do you think?
I'm sorry, I might have the definitions mixed up, but did we start with inductive reasoning, but then end on deductive reasoning?
Okay, so we have inductive reasoning. So inductive reasoning starts with patterns, which is what you're identifying. We started with patterns, right? And then what happened at the end is that we made a generalized statement, right? We assumed that the pattern was going to continue in the same way that we expected it to continue. And in making that assumption, we created a generalized formula that's inductive reasoning. It creates a general statement at the end, which is I think where you were going to, RJ. So this is inductive reasoning. Okay. Let's look at the counter to that. This one's going to be the deductive reasoning. I know I just spoiled all the fun because I told you, but you'll see the difference. We're going to using the nth term, find the first 5 terms. We're going to identify if the sequence is arithmetic, geometric, or neither. Do you see the difference in how these questions start out? These questions don't start out with patterns. They start out with a formula, right? Over here, we started out with patterns and we created a formula based on what we thought we were seeing happening. Over here, we're told this is the formula, how you're going to find however many terms you want to find. Here we want to find 5. So we always start with n equal to 1. If I put in 1 here, what do I get? 11. How about if I put in, we have to find 5 of these, so put in 2. 16. Put in 3. Put in 4. Now, you're welcome to put in 5 if you wish, or you're welcome to notice that you've now created a pattern and you probably know what comes next. 11, 16, 21, 26. What comes next? 31. And if you don't notice that, or if it feels funny to say it that way, then just write out the last one and you're going to get 31 as well. Okay? Now, looking at the sequence we created, 11, 16, and so forth down that list, arithmetic or geometric? It's arithmetic. What are you adding?
5.
Sorry. Yeah, you're adding 5 every time. Exactly. Now, do you see in the formula why that's happening? Because there's a 5n, right? You're multiplying by 5. It's just like over here. The reason we got 3n is because we're adding the 3, so we multiply by 3. Yeah? Okay. This one here, a little different. So now we have n squared. So we're going to do 1 squared minus 1, which is going to give me, don't overthink it,
Is that 0?
that's 0, yeah. How about 2 squared minus 1?
3.
3. 3 squared minus 1. 8, yeah. 4 squared minus 1. 15. And then 5 squared minus 1 is 24. Okay? So these are our first 5 terms. Arithmetic, geometric, or neither? Is it arithmetic? No, we're not adding the same thing every time. Is it geometric?
No.
No.
We're not multiplying the same number.
Yeah. Geometric you can actually rule out really quick because you'd have to multiply 0 by something, and 0 times anything is 0, so you'd never get the rest of them. So if it's not arithmetic and it's not geometric, then it's what? Neither. This one's neither. And we will talk next time about what is happening with some of these, not all, but some of these ones that are neither. Because if I have this pattern, but I don't have the formula, there are still other ways to figure out what comes next, right? And I want to show you how to do that in a general sense. They don't work for all of them, but work for some of them. We'll pick up there next time. So this is deductive reasoning. I said it before, but this is deductive reasoning. We started with a actual equation, right? Not an equation, but an expression, and we used that to create our pattern. That's what makes it deductive reasoning.